Welcome to another session of control system, and today we are going to look at system performance. And what system performance entails is two responses. So we talked about when we were talking about the differential equations, we talked about the two solutions that are always there in differential equations. So we are just still going further into looking at how this actually the two solutions are. So when you talk about the system performance, then you are basically talking about the two solutions. That is what we refer to as the transient response, and also what we refer to as the steady state response. So those are the two solutions that we are talking about as far as system performance is concerned. So we are going to start by looking at the transient response. So that is the first thing that we are going to look at as far as system performance is concerned. So we are going to look at transient response. And later on, we look at the steady state response. So we are going to look at transient response. So when you look at, when you talk about the transient response, then basically the input control systems usually have, they may either be simple time varying quantities, or they may be complicated and random. In the testing of the systems, we usually have the standard signals, rather the standard inputs that are always used, and these are the inputs that we are going to talk about. So the standard inputs that are always used are, the first one is what we refer to as the step input. The step input. So when you talk about the step input, then we are simply talking about a sudden change. We are simply talking about a sudden change in a physical quantity, and this one usually occur ideally in 0 time. So when you talk about that, then we are simply talking about a system, considering that one, that is now the output. Then this one is against time. Then in that case, there is just a sudden rise in the output, and this one we can talk about in 0 time. So we are simply saying that that is now what we have, where f of t, the function f of t, is equals to a constant. So if somebody asks you what the step output is about, the step input is about, then we can simply say that it is a sudden change in value of physical quantity, and this one usually occur ideally in 0 time. But due to practical limitations, you'll find that it is always impossible to achieve this ideal step input, because we cannot have an activity happening in 0 time. But as long as the time within which the rise is occurring is after very small time, then we can usually refer to it as a step input. So provided that the rise time is very small, then we can refer to it as a step input. And that is now what the step input is. So you'll find that the step input is always, more of it is always used in order to obtain the transient response of a system. So basically, when we'll be talking about the transient response of a system, we'll be looking at it. More majorly, this is the input that we will be looking at most of the time as we go through the transient response. And of course, we'll also be looking at different inputs later on, but the most common one is this. So the second one that we can talk about, the second input that we can talk about is the unit impulse input. Unit impulse input. So the unit impulse input, then this one is just a special type of pulse in which it starts ideally at 0, at t is equals to 0. It starts ideally at t is equals to 0, and it usually has an infinite height. It has an infinite height and a duration again of 0 time, which means what we are talking about is, we are talking about an input like that. So this is the input. Then it rises to infinity. So for us to define it, we usually talk of it as unit impulse input. If we talk of the impulse input, then it has got infinite height, and we cannot define what infinite height is about. So in that case, when you talk about the impulse input, then we simply say that it is a special type of pulse which ideally starts at t is equals to 0, has an infinite height, and a duration of 0 time. Again, in practice, it is not very easy to come up with it. A perfect impulse input cannot always be achieved, and for testing purposes, we usually have what we call the unit impulse that is always used, and the unit impulse is a pulse whose area, the area of it represents 1 unit, and again, it has an infinite direction. So again, that is now what we can talk about as far as the unit impulse input is concerned. The third input that we can talk about is now what we refer to as the ramp input. We talk about the ramp input. We can talk about the ramp input, and when you talk about the ramp input in this case, then ramp input at times is also referred to as the constant velocity input. So the third one that we can talk about here is the ramp, into bracket, constant velocity inputs. So those ones are that is the input that we can talk about. So when you talk about the ramp or constant velocity input, then we are simply talking about an input function whose magnitude increases in linearity with time. The magnitude increases in linearity with time, rotation of the input at a constant angular velocity. And that is what represents the ramp input. So what we are talking about here is that whereby that is now the input and it is against time. Then in that case, that one goes in that way. So it is proportional, so that f of t is equals to, not really equals to, we can talk about is directly proportional to the function, whereby is directly proportional to the function time. So that is what the ramp input, or rather the constant velocity input, is all about. We said that we are going to make, the standard inputs that we are going to talk about are 5, so that is number 3. The next standard input that we are going to talk about is what we call the parabolic or constant acceleration input. The third one is parabolic or constant acceleration input. So we can talk about parabolic, number 4, parabolic, or what we refer to as constant acceleration input. We can talk about parabolic or constant acceleration input, and this one we are simply talking about an input in which the input control is always rotated at a constant acceleration. It is rotated at a constant acceleration, and that is now what the parabolic is about. So input in which the input control is actually rotated at a constant acceleration. So what do we mean by that? By diagram representation, we can have it that way, whereby we have it moving in that manner, and of course that is now the input, and there we have time, whereby we have the function f of t is directly proportional to t squared. So that is what the parabolic input, or rather what we refer to as the constant acceleration input, is all about. So that is now what we mean by that particular input. The last standard input that we are also going to look at is what we refer to as the sinusoidal input. We can talk about sinusoidal input. Sinusoidal input. So when you talk about sinusoidal input, then what we are simply talking about, we are talking about an input control that is subjected to a sinusoidally varying signals, and sinusoidally varying signals of oscillations, and these ones are actually the oscillations of the shaft, and it happens at constant frequency and magnitude. So when you talk about this, then what we are all just talking about is an input that is going to be sinusoidal, that manner, so that we have that. Then we can have this. that way. Then we can have the function f of t is equals to a sine omega t. So we have f of t to be equals to a sine omega t. A sine omega t. And of course, this one is now the input. And this is now the aspect of time. So that is what we can say as far as that is concerned. So those are the standard inputs that we can talk about as far as this is concerned. Those are the standard inputs that we can talk about as far as the inputs are concerned. So you should be able to describe all these inputs when needed, and you should be able to understand. Like we talked about the step input, we said that it is actually an input that takes ideally 0 time and it moves in steps. Whenever an input is increased, it moves in steps. Then we talked about the impulse input, whereby we talked about it considering a unit for where now we want to take the measurement. It will be easier if we consider a unit, because we say that it has got an infinite height, and the infinite height cannot just be defined. Then we also have what we refer to as the ramp or the constant velocity, whereby the input increases in linearity with time, and that one whereby f of t is actually proportional to t squared, and of course the sinusoidal input that we finished with. So after looking at the standard signals the standard input signals that are there, I want us now to look at the solution of differential equation. How do we get the solution for the differential equations? So what is going to aid us to get the solution for the differential equation is how we are going to obtain what we are going to use what we call the dimensionless equation. And the dimensionless equation, we want to look at how the dimensionless equation comes about, and it is for that reason why we want to consider a simple servo mechanism. So let's consider simple servo mechanism that we have there. So when you look at that simple servo mechanism, then it is always required that the output shaft is supposed to follow the rotation of an input shaft. So you can see that we have the two potentiometers, one at the input and the other one at the output. So you'll find that the angular positions of the two shafts are always measured by coupling the slider, and the sliders are this and that. The sliders, the two sliders, and these sliders are coupled. The sliders of the potentiometer, they are coupled to each shaft and then connected. Both of them are connected to their respective potentiometers, and this is done across a stabilized power supply. Provided that the two shafts, these particular two shafts have got the same angular positions, then there will be no potential difference. There will be no potential difference as long as they are they have the same angular positions between them. However, if there is any misalignment, if there is a misalignment, then a potential difference will exist. There will be a PD that will exist between the two sliders, and this particular potential difference will always depend on the sign and the magnitude of the deviation. They will depend on the sign and the magnitude of the deviation, and the amplifier in that case will then send the signal. It will then send the signal to now after that particular error, that is what is going to be between the input shaft and the output shaft. That is theta out and theta I. So this is theta out. So if you have that theta out and theta I, that particular signal will bring about the difference, and this difference is what will be amplified, and then the current sent through the armature servo motor of the field, of which will carry the constant excitation. That particular resulting torque that will be achieved as a result of that particular difference that we've talked about, the difference between the output shaft and the input shaft, then it will develop a torque by the motor, and this one will rotate the shaft in a manner to reduce the deviation that is there between theta I and theta out. So that is what is going to happen, and that particular difference, and this one will either bring the output shaft in the same position as to the input shaft or cause the output shaft to follow the input shaft. So that is why at times the servo mechanism is always referred to as a follow-up system, because it makes the input to follow the output. So that is what we can talk about as far as this is concerned. So let's consider a block diagram of the same, and we are going to use that particular block diagram in order to come up with the dimensionless equation that we are going to use in order to solve the differential equation. So that is what we want to look at. So we are going to look at the block diagram of this particular simple servo mechanism and use that particular block diagram in order to determine the dimensionless equation that ultimately we are going to use in order to solve the differential equations for this particular system, for several systems. So let's look at, let's have the block diagram. So this is actually now the block diagram of the same that we have. You can see that we have the KR, that is for the input transducer. Then we have the KR theta I, and of course here we have KR theta out, which means the error in this case, error will be given by KR minus theta I, KR into theta I minus theta out. That is what the torque, the error will be. So when you look at that, so we have defined what each and everything is. So we can say that the J is actually the total inertia of the motor, and the load that is referred to the load sign, kg-m squared. Then we also have what we call the viscous friction constant. And the viscous friction constant is always related to moving bodies. So this is a friction that is related to moving bodies, whereas we also have the other one, that is the T, which is the torque. That is the motor driving torque. Then we have Ka, which is the amplifier, transducer, or the conductor, the transconductance. Should be transconductance S. Transconductance S. So then we have the motor torque constant, A. We also have the transducer and the error detector. We also have the error voltage V. So those ones are what we are going to use. So let's look at how to come about with what we refer to as the differential, the dimensionless differential equation. The dimensionless differential equation. So we can look at the torque. So when you talk about the torque in this case, then the torque that we are actually talking about here, the torque will be given by T, is actually given by, the T will be given by Ka, Kt times the error. So that is the torque that we are going to talk about as far as this is concerned. So the torque will be given by that. Then from there, we know what the error is, but the error, we said that the error is equals to Kr into theta I minus theta out. So that is what the error is. And therefore, if we do that, then we can simply say that, if we say that, then we can simply say that, therefore, what we have here as the torque. So the torque, in this case now the torque, T, will now be equals to Ka, Kt, again, Kr into theta I minus theta out. Will be that. That is now what we are going to have as the torque. From the differential equations, we did define what is the moment of inertia. The moment of inertia. So that is now how we are going to get the error, that is the torque, that is torque T. And that particular torque T that we are talking about is given by that. So we say that the viscous friction and also the moment of inertia from the mechanical systems elements, that is what we dealt with in transfer functions. We did say that we can talk of the inertia torque. So the inertia torque is given by, you can talk of the inertia torque In this case, inertia torque, or what we refer to as the moment of inertia, is given by I as jd squared theta naught all over dt squared. So that is what we have for that, and that is the inertia torque and acceleration. So we also have what we call the viscous friction in that case. Viscous friction is given us, so the viscous friction in this case, that is the element of friction, it will be given us as from the mechanical systems under the transfer functions. We say that this one can be f d squared d theta naught all over dt. So that is now what we have. So in that case, from that now we have the elements that we can look at, and therefore what we can now see is that from this, if we now look at what we have for that particular system, then we can see that j d squared theta naught. So we can see that j d squared theta naught all over dt squared plus f d theta naught all over dt plus k theta naught is actually equals to k theta I. So that is the same as k theta I. So that is now what we can see if we look at what the elements are available as far as this is concerned. So from there we can find that if we assume that the total friction force and damping is F, and that needed for the system to be critically damped. For a system to be critically damped, then it means that it has got a damping factor of 1. So we'll see that also later on when we'll be looking at the responses with respect to the damping factors. So if this one happens, then we can now say that from there we can call this one equation 1. We can call that one equation 1. And if we call it equation 1, then we can say that F, from what we have said, all over Fc is equals to the value zeta, is the same as the value zeta, which is now what we refer to as equation 2, and this is now what we call the damping factor. So we are saying that if you are assuming that the total friction force and the damping is F, and that needed for the system to be critically damped is Fc, therefore F all over Fc is equals to zeta. And from there we can find what is Fc, where Fc is equals to, 2 root of zeta j. Zeta 2 root of zeta j. 2 root of zeta j. So that is what we have, and we can call this one equation 3. Can call that one equation 3. Equation 2, we have F over Fc is equals to that, and this is now what we call the damping ratio. So we can call this one the damping ratio. So this is what we call the damping ratio, and we can call it equation number 2. We can call it equation number 2. Without any damping, then the system will oscillate at an angular frequency that is given by omega n is equals to root of kj. If there is no damping, then it will oscillate at what we have as omega n is equals to root of k all over j. K all over j. And when the system is underdamped, then it will oscillate at an angular frequency omega d, and the angular frequency omega d, which is given by, as long as the system is underdamped, then it will now oscillate at an angular frequency omega d. And omega d is given by omega n root of 1 minus zeta squared. It's given by that root of 1 minus zeta squared. So that is how we get omega d. So if we look at the equation number 3, that is Fc, equation number 3, whereby we can now find that Fc is that 2j, then we can say that F now is going to be if we have that, then we can talk of equation number 3, which means f. F now is going to be, if you look at that, f now is going to be what we refer to as f will be, we say that f from there, f is equals to zeta fc. And fc, we said that, and fc is equals to 2, and fc is equals to, the fc is given by 2 root of kj, 2 root of kj. So which means f is going to be 2 zeta root of kj. And this one, we can call that one equation number 3. 2 zeta root of kj, we can call that one equation number 3. That one is from f. We did say that f is equals to, we did say that when the system is not damped, then f over, well, that is for this equation 2, f over fc is equals to that. But we say that fc is given by, that's the value, fc is given by that value, 2 root of kj. Then from now we can now get f, where f is going to be given by that. So dividing both sides by j, dividing both sides of the equation of the equation 3 by j. If we divide both sides of the equation 3 by j, then we are going to have f over j is equals to 2 zeta root of 2 zeta root of k all over j. If we divide it by that, because we are going to have the, if we divide them by j, so we are going to have j, so root j squared will give us j, so that is why we remain the root of j down. K is not affected, and therefore we are going to have that. So in this case, if we look at what was there for the representation of omega n, then we can comfortably say that f over j can now be given by 2 zeta omega n, because k over j is the same as, root of k over j is the same as omega n. So this one here we have root of k over j, so it will be 2 zeta omega n. And that one we can say that that is now a very, very important equation. So we are at that point. Again, we can now go to the equation 1 and divide both sides of the equation 1. If we divide both sides of the equation 1 by j, so dividing the equation 1 by j, dividing equation 1 by j. If we divide equation 1 by j, then it means that we are going to have j, that is d squared theta naught all over dt squared, so there is no need of writing j there, plus f all over j, f all over j, the theta naught all over dt, plus k all over j, theta naught is equals to k all over j theta I. So that is what we have for that case. But if you look at our previous equations, there was an expression for f over j. So what was f over j? F over j is 2 zeta omega n. So in that case, we can say that d squared, therefore, substituting f over j and k over j, the values for f over j and k over j, we know what k over j is. We know that omega n is equals to root of k over j. So it means that k over j will be omega n squared. So if we now, we can say substituting the expressions, substituting the expressions for f over j and k all over j. If we do that, then we can simply say that the equation will be, if we do that, then the equation will be d squared theta naught all over dt squared plus f over j. From that, we can see that it is 2 zeta omega n d theta naught all over dt plus k over j. We looked at k over j here. So k over j here is omega n. Root of k over j is omega n, which means omega n squared will simply be k over j. So that one we are going to have omega n squared theta naught is equals to omega n squared theta I. It's equals to omega n squared theta I. So this one is a very important equation, and this is what we refer to as the dimensionless equation. So this is what we refer to as the dimensionless equation. So given a differential equation in that form, if you are given a differential equation in that form, so that form, whenever we have d dt, or like that case of the theta squared naught, then we usually know that this is in time domain. So whenever you are given a differential equation in time domain, then it will be easier for you to solve that particular differential equation by using the dimensionless equation, as we will see in examples that, that we will do later on. So if we change, taking the Laplace transforms of that in order to get its overall transfer function, so we can go ahead and say the equation, taking LTs, taking the Laplace transforms. If we take the Laplace transforms, then of course you will find that that one will become s squared theta naught plus 2 zeta omega n s theta naught plus omega n squared theta naught is equals to omega n squared theta I. So we can say, we can put theta naught there, then we have s squared plus 2 zeta omega ns plus omega n squared, then the whole of this one is equals to omega n squared theta I. So getting the transfer function output over input, we are going to have theta naught is equals to theta naught over theta I will be equals to omega n squared all over s squared plus 2 zeta omega n s plus omega n squared. So that is now what we have in that case. So that equation also will be very, very important, especially when you are given a differential equation in frequency domain in order to solve it. So whereas this is what we call the dimensionless equation, then the denominator of the transfer function of the dimensionless equation equated to 0 is always referred to as characteristic equation. So what we are saying is that if this one we equate it to 0, such that we say equation s plus s squared plus 2 zeta omega n s plus omega n squared equated to 0, this is now what we call the characteristic equation. This is what we call the characteristic equation. So that is what we refer to as the characteristic equation. So when you talk about that, you say the characteristic equation. Therefore, yes, the characteristic equation is simply the denominator of the transfer function of the dimensionless equation equated to 0. So that is what we call the characteristic equation. You can continue. So depending on the amount of damping and also, as well as the frictional force in the system, the response to the unit step input may be either of the following. We can have we can have the response to be either of the following. For example, number 1, if so you remember the equation F all over Fc is equals to zeta. So this is where we are deriving all this. If F is less than Fc, so it means that F is less than Fc, then that one will be a fraction, and therefore it means that the value of zeta will be less than 1, and we can say the value of zeta will be less than 1, and therefore we can say that the system is underdamped. So this one we say that it is underdamped. The system is underdamped. So the system is underdamped. This is always used in servo systems, or we can say it is used in servos. it is used in servos. So that is what we can say as far as that is concerned. Then after that, we can say that if F is equals to FC, second one, if F is equals to FC, that is to say that zeta is equals to 1, then the system is critically damped. System is critically damped. So a critically damped system has got a value of zeta, which is equals to 1, and this one is always used in special installations only. So you can say it is used in special installations. It's always used in special installations only. It's always used in special installations only. And again, if F is greater than FC, the third scenario is that if F is greater than FC, then from that we know that it is always going to be greater than 1. That is to say that zeta is greater than 1. Then the system is overdamped. The system is overdamped. Then the system is overdamped. And if the system is overdamped, this one is hardly used ever. We don't rarely use an overdamped system. So we can say it is hardly used ever. Hardly used ever. Then finally, number 4, if F is equals to 0, that means that zeta is equals to 0, then the system is undamped. The system is undamped. Then the system is undamped, and it simply means that it is unstable. So in this case, the system is unstable. Can comfortably say that if that one happens, then we can say that the system is unstable. So these ones can be represented in terms of a graph in order to show how the response will be. So we can look at it in terms of a graph, and we are going to use the step input in order to show that. So we have that. So for the first one, the system is underdamped. We can say it starts from here. So this is the input. Then this is time. So it starts from here, then it oscillates until the end. It oscillates reducingly. So if the system is underdamped, then it will oscillate reducingly. So it will start with the bigger one, and the smaller one, then with the time it will diminish. So we can call that one number 1. If the system is critically damped, a system that is critically damped, we can use this to show that it will come to that. Then when it comes to that point along where the step is, it will be there. So that red one represents a critically damped system. In case the system is the third case, we are saying that if the system is overdamped, so this one is critically damped. Number 2 is critically damped. So if it is overdamped, then it will not reach even the step value. So it will come to that, coming there. Then before it can reach that point, then that is now where it is. So we can call that one, according to what we have said, what we have written, it is the number 3 there. And then if the system is undamped, a system that is undamped, now the oscillation will be forever. So if the system is undamped, then we are going to have this, then it will now be oscillating in that manner until the end. It will be oscillating until the end. There is no reduction in amplitude and there is no increase in amplitude. So that one is now what represents an undamped system. So notice there is a difference between undamped system, where there is no damping taking place, and underdamped system, whereby the damping is a fraction, that is a value that is less than 1. So those ones are the graphical representations of those particular types of damping as far as they are concerned. So the output solutions in terms of zeta and omega n for the particular kind of damping factors that we've talked about, that is the underdamped system, the critically damped, as well as the overdamped. These ones are the output solutions that we have for them. So that is the output for the underdamped. And the underdamped is what we have said that is mostly the most common one. So that is the formula that you use for the underdamped. So again, this is the formula that we will use for the critically damped, and this one is what we will use for the overdamped. So from what is commonly used, that is the equation for the underdamped system. From the equation of the underdamped system, there are some things that we are going to notice. We'll notice that if the value of zeta is increased in value, if we increase the value of zeta then we will find that there are several things that will happen. The first one is that the response will become less oscillatory. So if the value of zeta is increased, if we increase the value of zeta, then from that we'll find that the response will become less oscillatory. Response, number one, response will become less oscillatory. The response will become less oscillatory. What is responsible for the oscillation is from where the sign is here. And if the sign is this, then it means that the value of this, as we increase the value of zeta, this value will be becoming, as we increase the value of zeta, let's say an example of 0.9, maybe you take it to 0.99, then it means that whatever we are having there, it means that the oscillation will become less oscillatory. So that one is what we mean by that. Then the magnitude also of the overshoot will also decrease. What is responsible for the overshoot is that, and therefore when you increase the value of that value of zeta will be, the value here will decrease, the value here will again decrease, and if the value decreases, then it means that we are going to have the magnitude of the overshoot decreasing. So number two, magnitude of the overshoot decreases. The magnitude of the overshoot decreases. Then the other one, we can talk about the response time decreases. The time that it takes for it to respond, response time decreases. And then finally, we can say that the system will become sluggish. The system will become sluggish. The system will become sluggish. All these particular characteristics that we are talking about can be analyzed directly from the formula for the underdamped system. So the response time can always be reduced by increasing the gain of the amplifier. This one will always increase the omega n, and it will reduce the value of zeta. And if the value of zeta is reduced, then this one may as well cause instability. And therefore, it is usually recommended that a damping ratio of between 0.6 to 0.7 is always found to give a very fast response with the smallest overshoot. And therefore, it should be noted that the system has high speed of response if its time constant is small. A small time constant will give a high speed of response, and the time constant is given by 2j over f. So this time constant is given by 2j all over f, which is also just the same as 1 from what we talked about. The formulas will be the same as 1 over zeta omega n. So that is what we refer to as that. So basically, that is what we can do for now. So in our next meeting, we are going to look at the response of a second order underdamped system to a unit step input, and from there also we'll use all that we have learned in this in order to solve the differential equations that will be given. So we are going to look at the response of a second order, whereby we are going to look at the overshoot, what is this overshoot that we are talking about, what is the time delay, and what is the expression for the time delay, how do we calculate the time delay, what is the rise time, how do we calculate the rise time, settling time, and also all those others. And from there, we'll do the examples, and after the examples, we'll be able to understand better how to solve the differential equations as far as system performance and a transient response are concerned.